Hello, my name is Bruce Renouard, and I'm the CEO of FreeSwitch. I want to thank Bodo and Holger for allowing us to present at Bodo's Wide Bandgap Conference. We wish we could be there, but unfortunately we're in month 11 of the pandemic, and we are going to miss our friends in Germany and our other colleagues. So I'm going to start off by talking about how FreeSwitch can help make wide bandgap technology higher performance in EV cars. So to start off, let's talk a little bit about the drivetrain. Clearly, when we talk about drivetrains, we're talking about both the inverter and the motor together. And what many of you may not know is that the drivetrain is responsible for the dominant losses in an EV up until about 50 miles an hour. After 50 miles an hour, the biggest loss becomes that of wind resistance. When we talk about EVs, we talk about efficiencies and ranges. And we need to actually break that down into where motors are most efficient and where people drive. On the left-hand side here, you can see a white curve on the bottom of the Nissan Leaf motor efficiency contours. This white curve represents the amount of torque required for constant speed driving on level ground with no wind. And what you'll first notice is that the efficiencies at this end of the curve are falling off. And in fact, they're actually very inefficient in the neighborhood between anywhere as far as down to 75 to 80% efficiency. Now, unfortunately, this white curve is where people drive, which is what we show on the right-hand side of this presentation. This is the WLTC Class 3B. This is what effectively gives you the miles per gallon equivalent in an electric vehicle. And the driving profile is shown in red. And what you can gather from here is that very little of the driving profile is above 60 miles an hour. And there's a lot of time spent driving down here at the low torques, where low torques are required. And so if we can improve the efficiency in low torques in an electric vehicle, we can increase the range dramatically. So let's talk about what FreeSwitch is doing to help that. In today's inverters, there's a balance between how fast you can switch the transistors and the quality of the sine wave that they produce. And that balance is weighed against the motor efficiency data. And so the faster you can switch a motor, the faster you can switch an inverter, the higher the motor efficiency, but the lower the inverter's frequency. The result is, even though we're using silicon carbide in inverters today, such as Tesla and others, the switching frequency is still low. So what engineers do is they typically balance the motor efficiencies to the inverter efficiencies and find the sweet point, which is generally between 5 and 15 kilohertz for motors that are in the 150 kilowatts to 350 kilowatt range. There was an article that was generated in Nuremberg for the PCIM conference in 2017, which showed the improvement that could be had by making the switching frequencies faster, irregardless of the inverter efficiencies. So you can see in this case, at high RPM, the improvements are substantial, up to 21%, by going from 10 kilohertz switching frequency to a 25 kilohertz switching frequency. What we're going to show you is that we can move this switching frequency curve all the way out to 100 kilohertz and beyond with no impact to the inverter efficiencies. But before we do, let's talk about wideband gap. Now, I love wideband gap technologies, both GaN and silicon carbide. I've been personally involved with silicon carbide since 2011. And one of the key things that we were dealing with back then as well as now is that the fast transistor edge speeds create other problems. One is the degradation of insulation, shown on the lower right-hand side. The other one is could be an unbalanced system, which causes some electromechanical etching that take place in the bearings. Some manufacturers have even gone so far as to put a bearing brush on their brushless motors so that they can arrest these bearing currents. There's an additional problem with very fast DVDT, and what that does, it creates an overshoot. And then, of course, the switching losses in the inverters are often weighed against the motor efficiencies. And wideband gap still is using small and very low switching frequencies. For instance, the Tesla Model 3 is still switching at 10 kilohertz, even though it's using silicon carbide technology. And last is that in the case of silicon carbide, it costs more than silicon IGBTs. Now that gap is shrinking, of course, but it's going to be a lot more years before they're at parity. So let's talk about how we can improve the performance of silicon carbide in an AV. Before we get there, let's talk about the drawbacks and what are being done to solve the problems that silicon carbide introduces. One is, of course, there's still switching losses in silicon carbide. And so that means that typically people run the inverters at slower switching frequencies, which reduces the motor efficiencies. We'll talk more about that in detail. But that also means that you can't use high pole count motors, and that reduces the amount of motor power density that can be achieved. When we talk about the damages to both insulation and bearing damages, the solution within the inverter is often been, well, let's just add an output filter. Unfortunately, these output filters, even at 10 kilohertz and 20 kilohertz, are just way too expensive, bulky, and cost too much. So the solution in a motor has been to, okay, we'll put thicker insulation in the motor, but this actually reduces the motor efficiency and increases the cost of the motor. So what pre-switch does is we enable a forced resonance soft switching that takes place across all system, environmental, and temperature variances. Even if the devices change over time, we compensate for that within the algorithm. The result is that we can do soft switching across very fast switching frequencies and reduce the losses in silicon carbide for switching losses by 90 to 99%, and in IGBTs from 70% on up to 80%. Now we inherently solve the fast edge transistor problems that we talked about earlier, and we have built-in monitoring and simplified control within the chip. And we've also got a very fast DSAT protection because we're monitoring everything on a cycle-by-cycle basis. So the diagram to the right shows the forced resonant soft switching architecture known as an ARCP, invented by some engineers in General Electric. What we do is we use this AI to control the timing between S1, S2, D1, and D2 to ensure that there's 0 volts across both Q1 and Q2 at all times, at all switching cycles, both turn on and turn off. And to do that, we actually do the analysis on a cycle-by-cycle basis so that we're always adjusting on the fly for every cycle. I'm going to talk briefly about this algorithm. What you can see here in this GIF, and it may be hard to see on the screen because might be a delay, a lag between my explanation and this video, but on the right-hand side for the GIF, you can see the first 3 transitions represent the algorithm when it first wakes up. And what you'll see when this white line gets to these algorithms is that the current waveform that goes through the inductor is very large. And then as the algorithm realizes where it is in the design, in the switching states, it makes adjustments so that the resonant current through the inductors is always slightly above the load current. This can be done so you can make a pure sine wave, and again, it can be done on a cycle-to-cycle basis. We've switched up to 750 kilohertz. If you want more details on this, please go to our website. There's a full explanation there. What I'd like to talk about in this slide is the comparison between a hard switch silicon carbide transistor and a pre-switch silicon carbide transistor, both the same transistors. On the left-hand side, you can see an 800 volt voltage source, and you can see the current is not flowing. When the transistor turns on, of course, the current starts to flow, and you've got an overlap between the current and the voltage waveforms that results in an E-on of 2.5 millijoules. In the pre-switch case, you can see that we've separated the voltage and current waveforms here, and that results in practically elimination of the switching losses. In this case, it's 0.08 millijoules. This represents a 99% reduction in switching losses, and in fact, in most cases, we get to completely 100%. Now, if you compare this to the turn-off switching losses, again, you can see a very fast DVDT that occurs upon turn-off. And the voltage rises from effectively 0 to 800 volts, the current falls, and you've got a 1.25 millijoules loss in that one transition. Whereas in the pre-switch case, again, there's a separation between the voltage and current waveforms, resulting in a 0.013 millijoules. So effectively elimination of the switching losses upon turn-off. Now, the other thing you'll notice here is a big difference in the DVDT. Now, we're not trying to slide everyone, but there is a challenge here that this time scale is different than the left time scale, which makes this look more dramatic. But the key point is that we reduce the DVDT within the architecture because we're always putting capacitors across the transistors. And we can adjust those capacitors and therefore the DVDT to any value that you need when the customer specifies their system. So again, pre-switch eliminates 99% of the turn-off losses, and it's got a configurable DVDT. In summary, if you look at just the switching losses, you can see the comparison between the resistors that we're using for both turn on and turn off versus the hard switching. And you can see that for 3 devices in parallel, for the same 3 devices, both hard switched and pre-switched, you've got virtually a 0 switching losses compared to 11.27 millijoules of losses within the 3 switches in the hard switch application. But then there's an overhead that we have associated with our device that's actually the hard switching losses in the ARCP themselves. In this case, we're using IGBTs to turn on silicon carbide. And the result is that we have about a 0.21 millijoule overhead associated with managing the pre-switch timing. And so the net result is that we've got a 98% reduction in switching losses. And another key point here is that those switching losses that we do have actually occur in a different device and not in the working devices themselves. It occurs in the ARCP. So let's talk about what we can do with that. By eliminating the switching losses, we have established a whole new design freedoms that engineers can now take advantage of. If you look on this chart, you see the silicon carbide, the current through the silicon carbide falls as the switching frequency increases. We all know that's the case. But with the pre-switch application, when we manage it, there is a significant reduction, a significant increase in efficiency as a result of having no switching losses. And what this means is that you now have a full envelope that's above where you were with hard switching and where you can be with pre-switching that enables you to design anywhere you want within this curve. This green arrow to the left says that you can take this existing point of 10 kilohertz and now you can switch it with the same switching frequency and actually have a higher inverter efficiencies and or smaller and lower cost transistors. We'll talk more about that in a bit. You can also come significantly off to the right-hand side in terms of switching frequencies because now you're not impacted. And this gets you higher motor efficiencies. And it also enables you to have a higher motor fundamental, which gives you the option of having higher pole count motors. And that gives you a further increase in the power density within the motors themselves. So these new design freedoms are available for the engineer to choose how he wants to do and how he wants to take advantage of them. Now, one of the questions we get in this chart is a little bit deceiving, but one of the questions we get is what's the relative size between S1, S2, and Q1 and Q2? And what we want to show in this case is that when you look at the silicon required for a 200 kilowatt inverter, the amount of die area required for both half bridges in both phase 1, phase A, B, and C is dramatically reduced for the same efficiency. And if you account for the small transistors that we need here for the and diodes that we need for the soft switching ARCP out the topology, there's still a substantial die savings that can be had with the designer. And this directly translates to a lower cost inverter. This calculation is made with a 50% of the losses within the transistor coming from switching losses, by the way, on a 200 kilowatt inverter. Next, I want to talk a little bit about how higher switching frequencies can get you a cleaner output for the into the motor. On the left, we'll start off by looking at a Nissan Leaf inverter. This is running at 5 kilohertz, and you can see there's a big swing between the upper and lower of the current waveforms. Now, these current waveforms that are outside the fundamental do nothing more than heat the motor and don't provide any useful work or torque. And you can see on the bottom, the red areas indicate what's effectively an inductive heating that's taking place in the motor, whereas the rotational torque is generated by the fundamentals. So if we can eliminate some of that output ripple, and we can by switching very fast, we produce a much tighter and much more pure sine wave, what we call a CleanWave output. This improves the motor efficiency dramatically, and it can also result in more torque for the same current. When we talk with customers, there's a clear understanding that in today, there's a balance between the motor losses and the inverter losses, and there's an analysis usually done that comes back to a center point. And because most engineers aren't aware that we can actually now eliminate these switching losses and push dramatically in new directions, we're locked into this existing thinking. We've been in some customer meetings where we've asked the motor manufacturers to come in and meet with the inverter manufacturers. And there starts to be a big discussion about how they would prefer really a pure sine wave to be generated and sent to the motor for the ultimate motor efficiency. But the key point in this chart is that there is an inverter savings. And when we talk to the inverter guys, this is really mostly what they're concerned about. But the larger savings is in the system level in the motor savings. And these system level savings are large, and in our opinion, it continues to improve even past 100 kilohertz, although the improvement gets smaller as you go higher in switching frequencies. So the key point is that pre-switch unlocks the capabilities of silicon carbide, and there's no penalty for using higher switching frequencies with pre-switch. When you look at the benefits of producing a almost pure sine wave into the motor, you can see that although the benefits are improved at the top in the right-hand case, there's a larger benefit, larger gains are had at the constant torques that's needed for constant speeds. So this directly increases and this improves the EV range by an estimated 5 to 12%. And we're actually working with multiple customers now that are designing our technology into inverters to prove this out. So the key point here is that the significantly faster switching frequencies can result in a much higher efficiency electric motor and increased EV range. I want to talk a little bit about our evaluation system. I know we've made some big claims here, and so what we've done is we've built an evaluation system that you can buy that is a 200 kilowatt, 3-phase inverter power block. And it takes an RS422 input here, plus a 15-volt power supply, and it produces AC out and DC with DC in, and it's bidirectional. This inverter is 99% efficiency running at 100 kilohertz, and it still produces 61 kilowatts per liter or 1,000 watts per cubic inch. If you look at this system, there's a significant amount of air and wasted space in it because it's just an evaluation system. And it's designed to show people what the pre-switch technology can be in their design. We encourage customers to buy this so they can start writing to our interface through the RS422 and see the algorithm adapt in system across all known and unknown changes that occur within the environment or within the inverter itself. If you strip off the top control layer and you get down to what we call the RPG, this is the resonant power gate driver, you can see the top of this chart represents 18 silicon carbide MOSFETs. There's spring steel holding them down, and there's 3 MOSFETs per switch location and 6 per phase. The resonant caps that we add for the forced resonant soft switching are 1 nanofarad each, and they're very small. The inductor is also small. It's basically 380 nanohenries, and it's an RM8. The other thing you'll notice is that these capacitors represent the full DC link capacitors, full DC link capacitance necessary for this design. Now, the reason they're so small is because it's running at 100 kilohertz, so you get an additional savings by running very fast switching frequencies. On the bottom, you'll see that there is a, these are where we have the resonant diodes and the resonant IGBTs that we use to soft switch the silicon carbide MOSFETs. On the left-hand side, this represents what we call the mid-rail balancing. It's what keeps the voltage source in the middle of the ARCP algorithm, ARCP topology to be right at the mid-level of the voltage so that we can get accurate soft switching. On the bottom, of course, is the DC input, which could be up to 900 volts. So with that, I would like to introduce to you Jimmy Palmer. Jimmy is the lead engineer on the CleanWave evaluation system, and he'll talk you through the CleanWave running in our lab.
So hey guys, this is Jimmy Palmer at FreeSwitch. This is our CleanWave 200 evaluation unit. We're running at 38.6 kilowatts, calculated 3-phase power in full bridge mode. We're running at 100 kilohertz, 500 hertz on the middle. And our calculated efficiency is 99.2%. That's based on this the loss from the power supply. Since we're running circulating the power, this is just a supplied loss. Here you can see that the devices are pretty cool while running 50 amps RMS through them, and the hottest parts are actually the pre-drum board on top. All right, thanks for checking us out, and more to come at FreeSwitch.
So just a minor correction, the calculated efficiency was turned out to be 99.1% in this application. But the key point here is that the losses are not in the devices themselves. They can be switched very fast and very efficiently. So in summary, FreeSwitch enables a new inverter paradigm where you can have high switching frequencies and high efficiency in the motor and high efficiency in the inverter at 100 kilohertz and above. We solve a lot of the bearing problems and installation problems associated with electric vehicles. We can give the EV an additional 5 to 12% more range, and it's a lower cost system at the system level. Lastly, I did want to say is we've got superior protection and very fast DSAT and over voltage protection and temperature protection. So there's more information available at preswitch.com. We appreciate you staying to the end of our presentation, and we hope everyone is staying safe, and come see us at FreeSwitch. Thanks again for your time.